Good morning, everyone, and welcome once again to another session of the Friday seminar series. So before we begin, on behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners of the land on which we meet today, the Turrbal and Jagera people, and pay our respects to their ancestors and descendants who continue cultural and spiritual connection to country. It's my great pleasure today to introduce Mark Drechsler. So Mark is the founding director, or one of the founding directors of CBSM Mining Services, who are developing wet and dry tertiary to quaternary GRolls crushing technology for the mining, cement and waste industries. So Mark is an engineering geologist with over 40 years of experience and has conducted research into green geopolymer concrete and the sustainable use of waste materials such as slags and fly ash for the construction and cement industries. So Mark leads the commercialisation pathway for CBSM and is involved in the design, development and testing of the laboratory and pilot scale GRolls unit and collaboration with research organisations. So please join me in welcoming Mark today.
Morning all, thank you. Yes, yeah, I'm an engineering geologist. So I got into Comminution via a long path. I used to work for a company called Readymix, and we were involved in the cement, concrete, and quarrying industry. And so and that was about 20 odd years ago, and I started looking at applications for green concrete and looking at reducing the Portland cement contents in concretes because concrete and cement is one of the highest greenhouse gas emission products in the world. 5 to 8% of our greenhouse gas emissions come from cement production. And so one of the challenges I found is that when using waste materials is you need to reduce their fineness of the material to get that they're more reactive. And so I started looking at what technologies were available to reduce slags, fly ashes, and recycled materials into much finer products. So that's how I got into the Comminution technology, and I got into that about 9 years ago now. And so as part of that, developing this new technology with some partners. So that's a bit of a background. So yeah, so Bill Skinner, are you online? Bill Skinner is a research professor at the University of South Australia. He's also one of our shareholders, but also we're putting our unit into the University of South Australia and doing a whole lot of research testing with them. Hopefully the technology works. So Comminution is about making big rocks into very, very small rocks and targeting the size of rocks or particles that you need to in the mining industry is to extract all those valuable minerals. In the cement industry, it's about getting very, very fine, so you get a much greater surface area. But the theory is very, very similar. And when you're breaking big things into small things, you need lots of energy. And as you get your target particle size gets smaller and smaller, you need much more and more energy to actually achieve that. So this graph just shows a representation of how much energy, the steepness of the energy that you need once you get into the tertiary and quaternary crushing or comminution phases. Trying to get those really fine particle sizes, you need to use a lot of energy to produce those particles. So in a typical mining operation, a comminution takes about 10% of their power consumption. And mining a comminution around the world accounts for around about 1% of global power consumption. So that 10% of a mining operation accounts for about 1% of the global power consumption. In the cement industry, comminution, again, that accounts for around about 70% of a operator's cost. And again, that accounts for around about 1% of global power consumption. So comminution is a very energy intensive, very power intensive, and very costly part of a mining and a cement operations. And with power prices going up, and we're all feeling that pain, is going to get more and more. Also, another large cost for a mining operations is media, which can be up to 17% of a cost, and that's something that's a hidden thing. Well, not hidden, but it's a factor that just is there, and people don't sort of realise how much cost the media, that for a mining operation. So these are all the current comminution type technologies. So going from the top, you get very coarse feed, and you get down, and obviously when you're trying to the technology is very difficult to get all in one pass to get down into your really fine. So you have a series of crushing and comminution technologies. So you go from your primary crusher, which gets the real big rock from the mine and that, and then then you go through a series of crushers and then mills to get to the really fine. And so each of those technologies has got a nice sweet spot where they operate really well. Beyond that, they struggle on that. So this gives a bit of an idea. So at the top, you've got your ag mills and your sag mills. So then there's probably then there's rod mills. But then in the middle here, we've got HPGR. So HPGR is high pressure grinding rolls. And then the VRM is the vertical rolls mills. And these have started to come into the mining sector as comminution units. And I'll talk about that more later on. And then as you get further and further down, so they can take some quite coarse feed. But then you get down to the more of the specialists, the ball mills and the stirred mills, and then the vibrating mills and that sort of thing. So talking about trying to achieve those really, really fine particle sizes that some of the products need, or some of the ore bodies need. Just a quick snapshot of the comminution global market. It's about a $2 billion a year market in 2020. So ball mills is about a third of that market. Now, ball mills are the traditional. I'm talking about ball mills, sag mills, AG mills, and in a sort of a similar sort of vein. They're all lumped in there, and so they've been the traditional main comminution for tertiary and quaternary. But what we now have is large proportion of that has been taken up by HPGRs and VRMs. HPGRs and VRMs were actually developed in the cement industry and have slowly progressed into the mining industry, and so they're starting to take some of this ball mill market share. VRMs were extensively used in the cement industry, but now the cement industry globally has peaked out, and so those VRM producers are now looking for new markets to penetrate, and so they're now pushing into the mining industry to provide products into the mining industry. So the VRMs had already had a very large market share, but that was mainly up until the last 3 or 4 years concentrated on the cement industry. Now they're switching to the mining industry. And HPGRs have been in the mining industry for a while, and again, that came from the cement industry, but they have a lower proportion. And then others, your iso mills and your stirred mills and all these other sort of technologies. The International Energy Agency in 2020, while they go through quite a few years every year, do a report. They produce a report on the role of critical minerals in the clean energy transitions. And we all know about meeting net zero goals by 2050 and the need to increase our renewable energy requirements. And so critical minerals are as the name suggests, critical to that. So the IEA identified several key risks to meeting those goals by 2050. First, one of those things is there's a declining ore quality, and ore bodies are more complex, and they also, and then they, as a result, they have increased and multiple challenges to actually recover those ore bodies. So yes, the easy ore bodies have been taken, and we need to get more and more to continue to get more and more materials. We need to go into lesser grade, but also more complex and also more remote. It takes 17 years from a ore body to be discovered to actual production. So if we're to meet 2050 goals, if you take away 17 years from that, that's 2033. So by we need to make sure that we are discovering minerals and resources all the way through to actually meet those goals. Because if we find something in 2050, well, in 2040, unless we can shorten that discovery to production time frame, we won't meet those goals. ESG is a growing imperative because of all the energy costs and efficiencies and renewables. And you see there the copper energy, the cost of energy as per the mining cost is around 20% for copper. Nickel and iron ore is around about 8%, but there are huge costs to that. Half of the global lithium and copper production are in areas of high water stress. In other words, there is not much water in those regions or locations. So there's large deposits, but they haven't got much water. So how do we deal with that? And in high water stress, that means there might be sufficient water, but there's many users as well. And so having a mining operation to come in and actually take some of that water creates additional stress to an already stressed location. So that's a huge issue. And finally, to meet those net zero goals, we need to increase our mineral demand by sometimes up to six times for some of those critical minerals. It's reported that copper production needs to increase threefold, and lithium needs to be increased 12-fold, and some of these other more critical minerals have to be increased by 40-fold to meet those net zero goals. So that's a huge pressure, and the mining sector is increasingly more critical to meet those net zero goals. Rather than reducing the mining sector, we need to actually increase it. But what we need to do is we need to change the focus of the mining sector from carbon emission products such as coal-fired power generation coal to more renewable. So the mining sector is needed. So what are mining trends across the world? Well, mining companies are committing to reducing their emissions. High-grade projects in low-risk jurisdictions are hard to come by. So in other words, all the best ones are already taken, so it's going to get costly more and more. It's going to take more and more. Reserves are located in remote locations, remote to energy, water, and transport. So those reserves need more infrastructure to actually get to them. And as I said before, there's declining ore qualities and more complex ore bodies. So how's the mining sector meeting those trends? HPGRs and VRMs are now starting to be used for dry circuits in the mining sector. So in other words, trying to reduce the amount of water used in those projects. The use of agile plants, in other words, trying to go into smaller smaller volumes, pick those materials out and then move on. So that's called agile plants. So instead of going for really big, massive plants, slightly smaller plants that can maybe spend 5 or 10 years at a site and then move, rather than something there that's for 40 years. Trying to have a smaller footprint. So a smaller footprint is less tailings dams, less operation of the plant, those sort of things, but also, you know, a smaller footprint of those mining operations to the community. Reduced energy demand. So everyone, the cost of energy is going up, and so they're trying to reduce those energy. And then also the use of renewable energy sources for actually powering these plants. So in the last couple of years, there's been a few projects that have been announced that are starting to show these trends. Oz Minerals at West Musgrave in West Australia is going to be using 2 VRMs in a dry circuit, and they're going to be using 70% renewable energy, and they're going to have several satellite deposits. So they'll have a main plant, but then they'll have several smaller satellite deposits which will then feed into that main plant. So they're going to a dry circuit. So that's a copper. I think it's a copper. Yeah. CIMIC Mining in South Australia, they're looking at for their magnetite expansion, again using VRMs. So for crushing their magnetite ore. And in Grange Resources South Down deposit in West Australia, again using 2 VRMs. So instead of using ball mills and SAG mills, they're using VRMs to have a dry process as much as possible. So if we look at that pie chart before of the plant costs, if we move to a dry process, we're reducing our power consumption by about 30% by using the VRM. So we take about 3% off the power chunk, but there's no media, and so that's a huge chunk of cost. But also going to dry is actually showing that it's actually improving the ore recovery from that 1 or 2%. And so you get not only cost savings in the operating, but you also get improved ore recovery. So that's the general trends in that. So let's just talk about how we got to my involvement and the technology that we're developing. Grinding and attrition is a very energy-intensive process in mining, and we all know that. And so what we looked at is, you know, crushers are a more energy-efficient way of reducing particle sizes, and they require no media. So crushers are used in the primary and secondary, and sometimes in the tertiary, but they're not targeted for getting down to those really fine to ultra-fine sizes that the mineral processors need to recover the ore bodies. So we looked at how can we extend those crushing forces into tertiary and quaternary circuits to produce fine to ultrafine particles as far as technically possible. So our target was to produce a technology that can produce a high percentages of less than 100 micron in a single pass. By doing that, you're reducing the recirculation loads and that. It can be used both dry or wet. Most comminution technologies are either dry or wet. They can't be both. Having no media, that's an important thing. Being energy efficient, and hopefully the use of the crushing forces helps that. A simple design, a manufacturer, modular, and can be scalable, so we can get into those agile plants. So that's where we developed the concept for the Gyratory Rolls Crusher. So the Gyratory Rolls Crusher is basically looking at what are the disadvantages of HPGRs and using the crushing technology to develop a new technology. So what we've got is 2 rollers, rotating rollers, but the rollers are different. So a HPGR is a nice flat roller, so they're just using compression only, and they're just using brute force. We want to produce crushing forces, and so we've actually changed the shape of the rollers to be these chevron shaped or V-shaped with interlinking shapes. So as you can see here on the right-hand side, so what you're actually producing is multiple crushing chambers within a single unit. So instead of having a nice flat plate and then the crushing, we're actually producing lots of different crushing chambers within a single unit. And so those crushing chambers operate much more efficiently. So what we do is we have the main roll rotating and dragging material in, but we have the other roll actually oscillates or vibrates, and it actually vibrates in a very small distance, and so it actually gyrates, so it actually creates pulses, so it goes in and out against the main roller. And so we've got eccentrics that are 100 micron to 500 micron in size. So when you look at a normal cone crusher or a primary crusher, jaw crusher, you know, they've got open size and close size settings of, you know, inches and that sort of thing. So we're looking, because we're targeting the very fine sizes, that's why we've got those very fine eccentrics. And this gyratory roll, it oscillates at about 1,000 RPM. So it's very, very quick, very fast. So these are all the forces, and, you know, part of the pushing the crushing technology into there is that, you know, you have different compression, shear, and tension. And so here is the jaws, the rollers, and as a particle passes through, or might actually migrate through all that, they're subject to different shear and compression forces. So that's how we get that energy efficiency. So HPGR is purely reliant on compression. We have shear, tension, and compression. So that's how we can be, we believe, will be much more energy efficient. So these are the rolls when they're nice and brand new. And this is a lab scale unit that we have built to test the concept. It's an alpha prototype. So built the rolls not with hardened faces, so that we can see what the wear is like over time. And this is the unit. So it's a skid mounted. It's got a control unit. It's a little lab scale. So it's the rollers are 400 wide. We can feed materials anywhere from 200 kilos an hour to up to 1 ton an hour. It will take up to 20 mil feed. It bounces around a bit, but it still does it. We haven't retried anything bigger than that, but as we think, you know, upscaling, we can get a larger feed. And the unit's about 2 meters, and that's skid mounted, so we can use it dry or wet, and it's good for laboratory sizing of bulk exploration samples. You can put materials through, but also you can test your product going through, and it actually replicates the process circuit quite well. So you don't need other test methods to actually sort of try and correlate and stuff like that. What you put in, you measure the energy, and that's the energy consumption, and the product that comes out, that's exactly what you would expect in the process. So we've done trials on a whole lot of different feed materials. We would like to trial more feed materials, but so this is limestone, silica sand, a slag material, and then a magnetite ore. And they all generate quite high. So here's your 100 micron grading size. So generating quite high percentages, 20 to 40%. That 100 micron. Sorry, I've had a colder week, so talking, starting to get it going. So then we looked at, you know, changing the feed material sizes and see how it improves and that. So by going coarser and coarser material, so we're still getting a very high fines generation, when we're going coarser. So that's up to 10 mil feed. We're getting very similar material coming out the bottom end. So going through a whole lot of feed sizes, and one of the things about comminution is trying to see how much your reduction ratio is, and how the reduction of your particle size as a single pass and all that. And so what we done was we plotted the reduction ratio here. So on the left-hand axis in the blue bars. And so under feed material of 2 mil or less, we were getting to 2 and 3 reduction ratios. So that's not too bad. But when we fed between 2 mil and 20 mil, see here the reduction ratios dramatically increased. And so this is probably the sweet spot of the unit, this lab scale unit. And so in other words, a reduction ratio. So in other words, this P80, F80, a feed 80, a feed material which had 80% 5.1 millimeters, a reduction ratio of 19 means that it then went down to around about 40 or 400 or 300 micron in a single pass as a P80. So it's working really, really hard. A HPGR normally gets around about 4. Now, HPGRs normally don't operate in the minus. They don't normally receive feed less than 2 mil. So they normally receive feed between 50 mil and 100 mil. So they're getting reduction ratios around about 4. So we're getting much higher reduction ratios. And that's because of the energy being used and the different shearing and the different crushing forces is much more efficient. And as you can see that even when we get really coarse material, the fines generation is quite high. These peaks and troughs are probably because of different hardness of the material, but you can still see getting quite high percentages of fine material. We crushed some magnetite ore, and we got a very high fines generation, 38% generation of a 10 mil magnetite ore in a single pass. When we compare that to a HPGR, the HPGR only got about 18%. So in other words, we got more than twice the amount of fines generated in a single pass than a HPGR. So that's a very encouraging, and that works by actually reducing the number of recirculation loads, and there's less air classification needed. So therefore, there's lower power consumption per ton of product. One thing we did was we looked at the different configurations of the unit and seeing how they impact on the performance. And we changed the main drive speed, and this was quite a interesting chart. And so remember, the main drive pulls in material into the unit, and so that speed is changed. And so when we had really high speeds, we were actually generating much higher energy consumption for those, but also lower productivity for those high speeds. So when we dropped them down, we found there's a bit of a sweet spot where we have very high production rates. So this is the percentage of the target, 75 micron. So that's increased. Our energy consumption has gone down, and so the grey bar here, and so reducing in speed. So there's significant power increase with increased speed. We think that's because of increased speed, you're going from crushing and shearing and that to straight crushing and trying to jam the material down through that gap, and so you're exerting lots of energy. But again, if you look here, that there will be, as you slow it down, you're actually starting to increase your energy requirements. So there's probably a sweet spot here where for a certain drive for that material. So for each of the materials, you do a whole lot of working on it. So, and this is the revolutions, so the main drive speed. So what you try and do is match the amount of oscillations of the gyration against the main drive to get that shearing, tension, and compression as much as possible. When we did, so that previous slide was for minus 9.5 mil. When we went to the more coarser material, we found that dropping the speed, you actually reduce your productivity and your energy, and so there's slightly higher. So you need those slightly higher because of the bigger materials. So what it suggests is that every material you need to do a whole lot of tests to work out which is the sweet spot. And we got in the GRolls, we got 3 main configuration levers that we can change the performance of the unit, the main drive, the oscillation speed, and also the applied load. And so, like a HPGR, the rollers are actuated against each other, and so there's mechanisms that if it bogs down or jams, that you can release. So that applied load is a factor as well. So that was all dry tests, and that worked very well. And then we wanted to prove the concept that we can use it in wet, and so we used the same material, and this is we used a minus 3 mil limestone material to basically replicate a refeed material from a mining process going into a regrind circuit and stuff like that, and seeing if we can replicate that. As you can see, that the dry grading and the wet discharge were relatively similar for the same material. So we're getting quite high percentages of fines. But interesting fact was that the slurry that we went through at 4 times the rate of the dry feed. So it actually passed through the unit quite quickly. So so this is the material going through dry. You'll see the rollers moving around. It's actually quite slow. This is slowed down. And then this is the slurry. So this is the same material, but in a slurry, in a 33% slurry. So yeah, so that's so what we've shown is that we can actually slot the GRolls in amongst all our competitors, all the existing tertiary and quaternary comminution circuits, and we can do it both dry and wet, and we can get down to that 10 micron size. So we developed a concept design for the upscaling of the next size, and so we got a lab scale, but then we need to commercialize it, so we need to upscale on that. So that's what we've developed as a 3 to 5 ton unit. It'll be able to sit in a truck or in a container. It can be used. We haven't shown all the bin, and this is mainly just the main configuration with the actuators, the main drives, the rollers here. And so that unit, will be used for wet and dry circuits. We can add it to existing circuits and take feed from, and then feed that material back into it. Or we can do on-site testing of bulk exploration samples, or it can be used in small-scale mining and artisanal operations. And then what we plan to do is have that 3 to 5 ton that then proves the commercial unit, commerciality of the technology, and then we'll start building larger units, progressively larger units. So in summary, believe our GRolls technology can achieve similar energy or media savings to HPGRs and VRMs in dry, tertiary, and quaternary circuits. We can actually operate in wet regrind circuits, and we can even process tailings. And there's a whole focus on going back into tailings dams and winning material from old tailings. It can be modular and mobile because the unit, the way it is set up, it's much smaller than the HPGRs and VRMs, and so therefore it's more suitable for agile plants and that. But we've also got units that were mobile laboratory and small scale units. We can use them for pilot plants, use them for exploring and then testing critical mineral resources. I'd like to acknowledge Chris Kelsey, who's the inventor of the technology, who passed away last year. And other acknowledges the South Australian government and the shareholders. And that's it. Thank you very much. Any questions?
All right, thanks, Mark. I'll open the floor up to questions now.
I've got another small short video of it crushing some material if you want to watch that beforehand.
Yep.
Hopefully it works. So this is 20 mil, and you can see that it's going into the crusher, and you can see that there are all different little crushing chambers in there, and you can see the material getting compressed into those pinch points. So that's what happens in a coarse material. When you do a fine material, you have more material on those surfaces doing shear. So coarse material, you're more probably doing compression. And so, yeah, looking brute force. But it's very similar to a primary crusher. If you look at a jaw crusher and stuff like that, it's very similar. But what we try and target is the very fine product size. Okay. All right.
All right, so we'll start with an online question that we had. So this question comes from Paseo. So HPGR rollware, roll surface design and material selection were important issues with only compression being used. Do you believe that the lining/surface protection and materials construction will be the main challenge for the success of this new equipment?
Yes, and it will be similar. You know, like all the wear is on those rollers, very similar to a HPGR. We haven't looked at, you know, different lining technologies, and there'll be different lining requirements for different materials, you know, and stuff like that. And so, yes, you know, that's where the wear is going to be. But I suppose the beauty of it is that, you know, it's a very simple operation to remove and replace those rolls, and so you could have liners that are less robust than that, so you have more sacrificial rollers and stuff like that. So and then pull them out and then put them back and then put new ones in, so replace them. So, you know, or you could laser bond them, or, you know, heat treat them. There's a whole range of liners.
Tom Evans here, Mark. Thanks. That was a really interesting talk, interesting ideas. I was wondering if you can look at the material that's come through the crusher and assess which particles have been, if there's a way of assessing which particles have been broken under shear versus compression, looking at it. Is that possible? And would, if you could, would it influence how you might tweak the design one way or another?
Yeah, it's a good question. That sounds like a good PhD, I reckon. I don't know. How you would do that. Having that shear and compression is both, and when you got materials of different particle size coming through, it would be difficult to and also delineate which ones just went through those faces, or which ones went through that pinch point where there's more of the compression. So I think maybe some 3D modeling and sort of simulations would actually demonstrate that more as well. Obviously those configurations of those rolls can be changed, and over time that's what we want to look at doing, and it'll really depend on the material that you are trying to put through as well. And there'll be a whole lot of different materials, and some will be finer, some will be coarser, some will have a whole range. So whether you want more of that compression or more the shear, but definitely the shearing and that sort of thing gives you more energy efficiency.
All right, we had another online question from Craig Brown. Is there a mechanism for dealing with stray metallic material in the feed?
Well, that would have to be done before, on the conveyor. So that's just a normal thing in the process plant. The process plant would have magnets on the conveyor belt. But the whole unit is very similar to other other crushing units. If there's something large and gets jammed in there, there's a release mechanism for the rolls to separate, and the feed then falls through. So, but obviously you don't want metallic materials going through, and because we're looking in the tertiary and quaternary stages, most of that tramp metal and all that would have already been picked up prior to that. So so we're so it's probably less of an issue, but it still is an issue. So we don't want those sort of things going through. And no technology wants that.
Mark, it's Tim Napier-Mann here. Thanks for the talk, and thanks for acknowledging Chris Kelsey too, because he was an extraordinarily inventive person. I remember him talking to me about this technology in the very early days. A couple of thoughts and a question. Obviously, you're going to try lots of different materials as soon as you can, and as the applications come along. And I would advise you to do that, because limestone is a really weird material, and it doesn't seem to, in the mineral processing world, behave much like anything else. Obviously, it's important for cement, but if you can get a few base metals through your device, that would be great. And my question is, one of the advantages touted for high pressure grinding rolls in some applications is not only is it supposedly energy efficient, but it produces a product that is weaker than it would otherwise be, and can go on to be ground by let's say an isomill or something with less energy than would otherwise be the case. So it might be worth taking your product and putting it through a standard grinding test to see if you get that effect on your device as well. Yeah.
Okay. Yep. Well, I suppose our target is to not need the isomill at the end. So isomills are extremely energy inefficient and stuff like that. And you only have a very small feed to discharge size of that material. But yeah.
And Bill Skinner, I've just elevated you, so you should be able to talk now.
Thanks. Nice to be elevated. Tim, your question is very, very pertinent. Full disclosure, I'm also a shareholder in the company, but with Chris Kelsey's previous design, which this is basically a different geometry, if you like, in various ways. You're right that it's not just necessarily doing the hardest feeds. It's making sure that you, for whatever the feed you are maximizing the subsequent processability, whether that be another stage of grinding or leach or flotation. So it's clear one thing is that all of these technologies, VRMs, HPGRs, GRolls, varying the amount of shear with compression means that you have potential for exposing more value, giving you a higher surface grade, if you like, for whether it's attachment to bubbles or its leachability. So that sort of work is easily shown. There was a question before about trying to see which particles have undergone fracture in different ways. I suppose that can be done with some amazing amount of SEM, if you like, sized SEM, but I think it'd be quite difficult. Certainly, we've shown that with similar technology, we can get higher leach rates at coarser sizes, which is indicative of a higher surface liberation. But I think there's a lot of coupling of this technology and similar technologies with either upstream or downstream unit operations that can potentially give you a bigger bang for your buck, in that you have a success in this area, and then it allows you to do some very successful things in other unit operations. So that's the exciting thing going into the future. But yes, Tim, building a good library of how the material behaves in this machine is very important. You can de-elevate me now.
Hi, Mark. Thanks for the presentation. My name's Kimrangi. I'm just wondering, you've done comparisons with HPGR, but what about the vertical roller mill, which seems to be a technology that it's probably more you're in competition with? Would I be right in making that assumption?
Yeah, probably. Yeah, it's difficult because HPGR, you actually get a test and you actually the product goes through in a single discharge. The problem with the VRM is that it's a black box, is that the VRM is set up is that the material recirculates as many times until it's let out at the particle size that you're wanting. And so you really need to look at the whole energy. And so so VRMs include air classification in all their energy calculations. So it's very difficult to get a single pass data, published data for a single pass of a VRM. And so it's very difficult to compare. And so you really need to compare is the VRM energy consumption versus a HPGR and a GRolls with air classification to get a similar comparison. And so that's the sort of difficulty, and to trying to get comparative net specific energies of 75 microns, and that is very difficult for a VRM because of that. But I suppose they're also just trying to keep their cards very close. But when you look at a VRM, they're huge units, very expensive. They're not mobile, and large energy consumers and that. But they are doing a great job for what they're designed to do. Is that pound the shit out of something until that particle says no, I'm small enough and let me out.
All right, and just a comment from Bill Skinner, just for the people online. So also the smallest VRM available requires 8 or more tons for a test. So we had another question online from Tanya Chamberlain. Do you have any partnerships with industry to test the next mobile unit on site to compare to what is currently installed on that site?
Yeah, we're going through a process of raising investment capital, because to build the next size unit up is probably close to $1 million, and then you got to operate it on site, you know, and the plan would be to operate it on a site for 6 months. So when you're putting 3 to 5 tons of material through for 6 months, that's a shitload of material to put through, but also to deal with, but also the cost and all that. And so that's our biggest challenge, is trying to get the capital. We have several mining companies that are interested in, once we get that large unit built on that, that we can put it into their process. We can situate it, and we can take feed material from their current process, put it through our unit, and then put it back into their process. So there's no loss of material, or that sort of thing. And so then they can look at the performance of our unit against their current technology. So we have several mining companies lined up, but our biggest challenge is actually to build the unit. Problem is that these things are quite expensive, so it's not like an app or something like that you can just do on your phone. It's a huge unit, needs to be designed and built and manufactured and that. So yeah, but we have several mining companies interested once we have that. So and getting that, as you say, getting those different feed materials and putting them through over a long period of time, seeing where the wear is, see how the machine breaks, try and break it, see where the maintenance is, see how long rollers last, bearings last, all those sort of things. That's what all the mining operators want. They want to know, and that takes time and that takes effort. So yeah.
We had another online question from Craig Brown. He presented info on magnetite feed. Many of these are bimodal with separate hard and soft components. Have you looked at the output in terms of the individual components?
No, we only had probably 50 kilos of magnetite ore to put through. So yeah, would be nice to get lots of material to put through and to do comparisons and stuff like that. But we can only put through what material that we can get. So hopefully the unit will be, our lab unit will be put at the University of South Australia, and then there will be opportunities for research partners to then use that unit. So we're hoping that we will then get access to a larger quantity, but also a more varied feed material, so we can build up that database of the different materials, different feed materials, different feed sizes, and different target products going through the unit, to get that understanding, and but also just do some fundamental research on it, which all takes time and money and effort.
All right, and then just another question from Craig Brown. Is there potential application as pebble crushing?
Pebble crushing? Yeah, well, we think that upscaling the unit, it will be able to receive coarser feed material, maybe similar to what HPGR and VRM can, and it really depends on the configuration of the rolls and those chevrons and that sort of thing. The small lab unit can take a 20 mil. It bounces around, but it still does it. You saw the video that actually use it. So if you have a larger unit with bigger rolls and all that, we think that it might be able to do some pebble, up to 50-60 mil, but we haven't tested that yet. So that's the beauties of looking at upscaling, sort of looking at how the configuration of the rolls relates to the feed size, and then the generation of particles. There's so many different aspects that we don't know, and that needs research. So yeah.
All right, and then just going back to the wear. So Mike Samuels has a question: is differential wear on the scrolls/rolls a concern for size up? I imagine there is significant consideration on the design of the feeder for the unit to ensure uniform distribution.
yes, feed distribution across, all. It's probably less critical for that slurry. You saw that the slurry, it actually sort of, I suppose, levels out itself and generates and leaks across and all that. But yeah, definitely a dry material, having that feed discharge across all the faces, and into all those chambers, is quite critical. And having uniform wear as well, those things. With the upscale unit, we've actually got the rollers. They will actually be built in segments, and so if wear in one part is more than another, you can take out that segment and then replace that rather than the whole roll. So they're all sort of options, but feed is a important part of having consistent material, leading to consistent wear across all the roller faces. Yes.
Hey Mark, Tom Evans here again. It looked like the crushers were oscillating normal to the axis of rotation of the drums. With this chevron-shaped design, it looks like there's a possibility that you could oscillate the crushers coaxially with the actual axis of rotation. Have you looked at that and how that might impact on, say, bearing design and bearing life and that sort of side of things?
Only one of the rolls oscillates. The main roll is fixed, so that doesn't oscillate. We haven't looked at making that oscillate as well. The one oscillation causes that gap, 1,000 times a minute. So that's quite, a very high frequency, very small. We've changed the rotation speed of the oscillation, or the rotation, the speeds of the oscillation. We've also changed the direction of the oscillation. We thought that, by having the oscillation going opposite to the main drive would keep material in the crushing chamber longer and stuff like that. It's probably not as important in the coarse materials, but seem to be in very fine feed. That sort of helps. So these are all, lots of variations that will be nice to play with and to look at, and maybe having a digital twin to actually look at all those sort of things, and the configurations, and that would be, that's part of our plan as well, is to have a digital twin so we can play around with the configurations, all these oscillations and the speeds and that, and just see how that impacts it. But it also impacts on the stresses of the frame, the bearings, as you say, all those sort of things. And we've only the lab unit that we got, we built cheaply because we didn't want to spend too much money on 3D design and go into the nth degree, because we wanted to prove the concept first. And so and we built that unit 3 years ago, using with normal materials, and over time we've broken it and replaced bearings and all those sort of things. So you, as a lab scale, you push it, you find out where the weak spots, you then fix it. So we've modified the frame. We've gone from a belt to a chain to a direct drive on the main drive on the main roller, to ensure that the feed is pushed in and provide better. So these are all learning things that over time and testing that you change and modify, and you learn from your mistakes and learn from trying things differently.
All right, we might have time for one final quick question from the audience here.
Thank you. Would you consider Gyratory Rolls Crusher in size reduction of waste material? Because recycling of waste material is not a current topic, and then grinding of batteries, electronic circuits is becoming a large topic. So maybe due to this shearing and nipping mechanism, and then it may be useful. Did you ever think about it?
Yes, very much so. You know, so I suppose that's where I came into it. You know, I'd look in the cement industry, looking at slags and fly ashes and all that, but also, you know, there's a huge amount of recycled concrete. There's also mountains of glass, you know, recycled glass, but also electronic waste. And so, you know, we haven't pursued those avenues because we haven't had the feed material. But yeah, more than happy to you know, if you have some material to put through and do all that sort of thing. So yeah, and that's what we see, that, you know, like most of the comminution technologies have many different applications, you know, in the cement and the mining industry and the waste industry. And so we believe that, yes, you know, our unit, because it can be done both dry and wet, and there's obviously going to be a real sweet spot, but also a real bad spot where you add moisture until it actually bogs or something like that. But then you add more, and then it's fine back again. So there would be there'll always be some feed materials that we may not be able to put through. But we haven't tried that, and we would love to. Yeah, definitely.
All right, well, I think we're all out of time. So thank you, Mark, for that very interesting presentation. And
Thank
please
you.
join me in thanking Mark.